Hello, my name is Ciro Pascasio, and I'm going to be talking to you about multi-threaded web servers. System design is a simple server with a thread pool, a mutex lock, an enqueue, a conditional signal, another mutex unlock, and then it reads the file from the hard drive. When multiple clients ask for your resources simultaneously in order to conveniently and efficiently provide them, you need to solve a delivery problem. Most modern web servers use multi-threaded to economize and maximize efficient use of their resources, making it possible to distribute resources adequately and concurrently for thousands of users, allowing us to have unprecedented connections, banks, text filing, vaccine distributing census, not to mention the immediate access to academic and medical information. My project is to exemplify the classical multi-threaded server implementation that allows us to maintain conveniently connected. Implementation. The client sends the file name and the server then reads the file and sends the contents back to the client, emulating how a web server works, but without the HTTP parsing. And current implementation does not have any access control list, allowing to read anything on the hard drive. Time comparison of a simple server for demonstration purposes only, with multiple threads using the simple server to call the server code from /temp/test files, having copies of the server.c file 1 through 5.c, and having 6.c being 10 times the size. Simple client requests the page. Here's a simple client written in Ruby, the local host on port 8989. Giving us the time. And a multi-client tester is a script that runs multiple clients querying the server. And we're gonna need to allow the backlog of more than one in the server. We're gonna be running it sequentially, requesting only one and multiple files at once. And multiple clients are taking more time. We can see on the right side of the screen. And here are the individual ones. So let's do something about it. Let's make it Pthreaded. # include pthread.h. And we're going to need to instantiate our thread, keep track, and provide a thread function, handle underscore connections and argument. Change the handle connection because thread functions need to return a void pointer, and not forget to return null so the compiler doesn't show errors. Running it gives us about the same time as before. So let's modify our old tester to give us each style request a round robin style. Some requests are taking longer, but in contrast, when done sequentially, you can see slow connections causes the rest to delay. Here on the right, we're seeing the single connections take about the same time as before, but like I said, when multiple connections are run sequentially, most of connections are taking about the same time, but they're taking longer than when done with a thread. Slow connections and bigger files cause delays on the other connections since they have got to wait. And you can really see the difference if you have access to a slower magnetic disk or another server or anything slow that doesn't tie up the processor. Asleep one to emulate the situation. In that example, you can see how sequential calls lag behind while multi-threaded thrive. Flood connections. If we flood the connections, it has one thread per connection, which slows down the server. Each thread is taking memory and CPU time, and sometimes you have got to mediate not to slow down your system. We're going to help it out with a thread pool. Start the thread pool with a size and declaring the array pool of threads. And declaring the array / pool of threads. Create the thread and we'll find the thread because we're gonna need to find our thread function because we want to reuse those threads and not just let them terminate. Input connection information and a queue so that the thread can query this and find it. Add the connections to the queue. Maintain the thread in a loop, and now we have comparable performance, but on the second time that we run it is running into a race condition. Therefore, it's not thread safe. What is happening is one of the threads gets desynchronized, one ends up faster than the other or some little thing. It takes the work that was going to be for the other and they start running into enumeration issues. To solve this, we're gonna initialize a mutex lock. It's gonna keep them locked from both sides right before the queue and unlock it right after the queue, so they don't start getting desynchronized or having run into these race condition problems. Working with the Mutex locked multi-threaded server is slow, but now for unlocking and unlocking, we have a multi-threaded server that's up and working and not crashing, but it's still hogging CPU resources. CPU cycles and the way to work. Having your thread checking all the time if there is work to be done in the queue is not effective, for it uses all the available CPU cycles. Trade-off between CPU overhead and responsiveness. More responsive, shorter sleep times, check queue more often, uses more CPU. Less responsive, longer sleep times, check queue less often, uses more CPU. Pthread condition variables lets thread wait for a signal, not unlike semaphore, for it to effectuate some work, and are here implemented to allow the threads to wait for the process and not use all available CPU cycles. The condition variables are designed to work closely with the mutex locks, and therefore that's why you have to send the mutex when you wait, because when you wait, you're also releasing the lock. It's right here. I'm gonna instantiate it, and yeah, it's also gonna be right after the queue, and he's right before the queue. Memo. Pthreads are stateless. Threads are waiting each time for the loop, and main thread is signaling each time a new connection comes in, but when we have many signals, we can see a flaw. When it calls wait, it waits regardless of how many times it has been signaled before it waits. If threads aren't keeping up at some point, there is no new work added to the queue, so signal isn't being called anymore. But there is a lot of work still in the queue, and worker threads are finishing the task and they call wait, and they are waiting. When many connections come, you can see the trouble, it just gets stuck. To fix this, you need to call the queue, and if it returns null when you call wait on your conditional, then you call wait on your conditional. If it returns, then you call null on your conditional. And then we ended up with working mutex locked conditional variable triggered servers. We have a working multi-threaded server using thread pools that doesn't run into race conditions, stacking up a bunch of threads, and that does not use all of your available CPU cycles, making our server attempt to deliver a decent service regardless of how big the request or delay in the request are. Thank you very much for your time. Any questions? Please.